Hello, statistics students, and welcome to section 4.3, where we talk about trees and counting techniques. So, if you remember, in section 4.1, we learned that when outcomes are equally likely, we compute the probability of an event using the formula shown here. So, just a quick review. 4.1, we learned about ways of coming up with probabilities. We talked about intuition. We talked about relative frequencies, or the empirical probability. And then this was the other one we talked about, equally likely outcomes, or sometimes called classical probability. So this probability of an event is the number of outcomes in which the event occurs divided by the total number of outcomes. So this formula requires that we be able to determine the number of outcomes in the sample space. So the problems we looked at so far, this has been kind of easy because the number of outcomes was small, or the sample space consisted of fairly straightforward events. But now we're going to look at ways of counting the number of possible outcomes in larger sample spaces, or those formed by more complicated events. And the note here is just telling us basically what we want to do. So we want to be able to determine how many outcomes there are without actually counting them. So sometimes there's just going to be too many to count. So we don't want to just go down the list 1, 2, 3, 4, because it's just not going to be practical. Sometimes won't even be possible. So we want to come up with other ways to do this. So when an outcome of an experiment is composed of a series of events, the multiplication rule gives us the total number of outcomes. So we use the multiplication rule in determining probabilities. Now we're going to use it in determining the total number of outcomes. So the multiplication rule of counting, or the multiplication principle, just says for a sequence of events where the first event has n sub 1 possible outcomes, the second event has n sub 2 possible outcomes, and the third event has n sub 3 possible outcomes, and so forth. So these n with the subscripts are just numbers, integer numbers. And we'll write down the formula here, but then when you see it in practice, it makes perfect sense. So in this case, the total number of possible outcomes for the sequence of events is n sub 1 times n sub 2 times n sub 3 times however many there are. You just multiply them all together. So let's say you've got, you can relate to this one, I'm sure. Going to go to the big math party. So suppose you have 4 pairs of pants, 3 shirts, and 2 pairs of shoes, and you want to know how many possible outfits can you wear to the math party. Now, whenever I ask my students about these math parties, they act like they don't know what I'm talking about, but I know a secret. Because one day in class, I noticed this student had a big M on her hand, a huge M, like with magic marker. And I said, well, what's that about? And she quickly said, you was at a math party and they put M's on your hand. And then I noticed when I looked closely, a lot of students are going to these parties because it seems like after the weekend they come back with these M's on their hands. So there's a lot of math parties apparently. I noticed that there are never English department parties, right? There's no physics parties, always math parties. So you'll be able to relate to this one, I'm sure. So you've got 4 pairs of pants, 3 shirts, and 2 pairs of shoes. How many possible outfits can you wear to the math party? Well, first, I'm just going to use that rule above, and then we'll make a probability tree diagram, and it makes it easy to see why. But so you're getting ready for the math party, and you're looking at your pairs of pants. You're like, well, I've got 4 pairs of pants. And according to that rule above, we can multiply that by our 3 shirt choices, and then our 2 pairs of shoes, which gives us a total of, when you multiply these all out, 4 times 3 is 12, times 2 is 24 outfits. So this time, let's do the same problem, but using a tree diagram. And the tree diagram makes it really clear why this works. Why this works in this case, and why the formula above works in the general case. So the thing is with a tree diagram, though, it takes a lot of work. So you wouldn't want to use a tree diagram all the time, but it's nice to see it once, so then you can see why this makes perfect sense. So let's say we've got a starting point right here. We're going to start here, and we're getting ready for the party, and we've got 4 pairs of pants to choose from. So we could go this route, let's say to here, or to here, or to here, or to here. So you got these 4 choices. So you're looking at your pants and you're like, well, let's see, I've got my Jordache jeans, of course. Super popular for math parties. Or maybe my Z Cavariccis, right? I'm sure those are popular. I'm about out. Oh, how about Levi's? If these pants are not popular anymore, maybe it'd be an 80s party and you'll fit right in. How about yoga pants? Can you wear those to a math party? I don't know. I just can't think of any other pants. Okay, so you got your 4 choices for pants. Then you've got your shirts to put on after that. So you've got, if you wear your Jordache jeans, then you've got your 3 choices. Let's make this easy. Let's go t-shirts. Red, white, blue. That makes it easy. So you've got your 3 choices for your shirts. I just labeled this first one, red, white, blue. And then all the rest are like that too. And then at the end, you've got your shoes. So you could be sporting your Jordache jeans with your blue shirt, and then you have to pick your shoes. You're like, hey, how about high top Reeboks? So you want those. Or, I don't know, Air Jordans. You guys might be able to tell I'm a little out of the loop. Actually, I'm way out of the loop. Okay. Did some bad planning here. I'm running out of room, but I think we can make it. So you can see why this makes sense, right? The formula is really easy to see with a tree diagram because you've got 4 choices here. At the end of each of those 4 choices, you've got 3 choices. So you got 4 times 3. So after you pick your pants and your shirt, you're going to have 12 possible branches, right? And then at the end of each of those, you get 2 choices for your shoes. So if you look at on the end here, there's 24 of these, we'll call them N branches. The name's not important at all. Just the idea that this tree diagram shows why this works. Because if you have to do a problem like this is going to be the way you want to do it, right? Not the tree diagram. But it's nice to see the tree diagram once, because then you can see exactly why this makes sense. So there are cases when tree diagrams are definitely nice to use when you're figuring out probabilities for certain cases, which we'll see. But for something like this, you can just use this rule. You've got 4 choices for pants times 3 choices for shirts times 2 choices for shoes, and you just multiply them all together. So let's look at one more example where we use a tree diagram. And in this example, we've got 8 marbles in a box. So I'm going to draw this over here. Let's see, we've got a box here. We've got 8 marbles. We've got 3 red marbles. We've got 4 blue marbles and 1 green marble, right? So 8 altogether. And we're going to randomly select 1 marble, note its color, and set it aside. So we're going to set it aside. We're not going to return it to the box. Then we randomly select another marble. And we want to make a tree diagram to show all the possible outcomes of the experiment, and we want to label the probability associated with each branch. So to start off, we start here. And when we pick a marble, we're going to get one of 3 colors, right? Either red, blue, or green. So when we pick a marble, I'm going to make 3 branches. So you could get this one, or this one. And let's say this one is red, blue, green. Okay, so let's think of the probabilities associated with this. So if I just randomly choose a marble out of this box, what's the probability it's going to be red? And you're probably thinking 3 out of 8, right? Because there's 3 red marbles and 8 altogether. So this branch, I have a 3 out of 8, 3/8 probability of going on this branch. Now the blue branch, there's 4 blue out of 8. So I'm going to have a 4 out of 8. I'm going to purposely not reduce it because it'll be easier to see something else if I don't reduce it. So I've got a 1/2 or a 4 out of 8 chance of picking a blue marble, right? When I pick a marble out of here. And if we pick a marble out of here, the probability we get a green marble, 1 out of 8, right? 1 out of 8. Okay, so these are the probabilities associated with the first marble choice. Also notice this. What do these probabilities add up to? Exactly 1, right? And we know that these are the 3 outcomes in our sample space. When we pick 1 marble, the outcomes are red, blue, green. And if we add up all the probabilities associated with those outcomes, we have to get 1, and we do. Okay, so now what we're going to do is set the marble aside and pick a new marble. So if we chose this red branch, if we picked a red marble first, then we pick another marble. So we have to think about, okay, we could get red, blue, or green. If we pick a blue marble, we could get red, blue, or green, and the green marble, red, blue, or green. So let me just fill this in. Okay, so here's where, stay with me for sure on this first part here. If I'm on this branch, that means I've already chosen a red marble, right? So if I'm figuring out these probabilities, these depend on me already picking the red marble. So if I want to figure out the probability of getting a red marble and another red marble, well, I'm on this branch. So on this branch, we've already picked 1 red marble. So on this branch, there are only 2 red marbles left. So when I'm calculating these 3 probabilities, I'm assuming we've already picked a red marble, right? We've already picked a red marble. So there are only 2 red marbles left. So under these conditions, what's the probability I pick a red marble? Well, now it's going to be 2 out of 7, right? So up here on this branch, 2 out of 7. So what about the probability to pick a blue marble? Again, assuming I've already chosen red first. Well, then I'm over here, so blue is going to be 4 out of 7. There's 7 marbles left. Remember, we're not putting the marble back. So right here is 4 out of 7. And then, of course, the green marble. Again, I've chosen red already, so we're in this situation is going to be 1 green out of 7, so it's 1 out of 7. Okay, so here's where what you should do is press pause and figure these out and come on back. Don't wait for me. That's the only way you can learn it. You got to try it yourself. So try it yourself and then come on back. Okay, so hopefully you pressed pause. If you didn't, press pause. Come on, you got to do this. All right, so to figure these out, we're not in this situation anymore, so I'm going to get rid of the red marble. Get rid of this part. Let me just rewrite 3 red there. So for figuring out these, we're assuming we've already chosen a blue marble, right? We've chosen a blue marble, so we don't have 4 blues, we have 3 blues. Right, so when we figure out these probabilities, we're assuming we've already chosen a blue marble. So since we're not putting the marbles back, we're setting it aside. We choose the first marble, it's blue, we set it aside. So here's our new situation. There's 7 marbles, 3 blues left. So the probability that I pick a red marble now is going to be 3 out of 7. Probability I pick a blue marble under these conditions, also 3 out of 7. And probability I pick a green marble, 1 out of 7. Now you may have noticed that these add up to 1, right? Because that's everything that could happen in this situation. So these probabilities of all the outcomes have to add up to 1. And what about these? They all add up to 1. What do you think these are going to add up to? Hopefully 1, but I need to change this. So because in this condition, figuring out these, we're assuming we've already chosen a green marble and then didn't put it back. So let's go back over here and erase this. Put the 4 blue back in there. But now down here, we're assuming we've already picked the green marble out. So the green marble is gone. There are no green marbles. There's just 7 marbles, 3 reds, and 4 blues. So here, the probability we get a red marble is 3 out of 7. The probability we get a blue marble, well, that's going to be 4 out of 7. And what's the probability we get a green marble? 0, right? Or 0 out of 7? 0 out of 7. Here's where I should probably mention something that comes up sometimes. If you ever forget, sometimes we forget these things. One of these is equal to 0 and one of them is undefined. Undefined for now. When you take calculus, you'll learn how to deal with it a little bit better. So this is okay, right? 0 over 7 is just 0. Here's the way to remember. What if you have $0 and you're willing to share it equally amongst your 7 friends? How much are they each going to get? $0. Now consider this. How sad would this be? You've got $7 and you are very willing to share it equally amongst your 0 friends. It's terrible. You don't even want to think about that. That's undefined. Right? Because you could read this as 7 divided by 0. We never divide by 0, right? We find ways around it in calculus, but until then, we never divide by 0. So 0 over 7 is okay, it's just 0. You could just put 0 there if you want to. I'm just putting 0 over 7 to keep it consistent, but 0 is fine. So these, again, add up to 1. And then we can use the multiplication principle to figure out things like, let me make some room here first. Things like, what's the probability we get a red and then a blue? Well, to get a red and a blue, here's what we're going to do. We're going to go on this branch and then this branch. And we actually can just multiply these two together. So the probability to get a red and then a blue is going to be 3/8 times 4/7, which is 12 over 56. And we can put that, I'm going to pick a different color here. 12 over 56. That's the probability that we would go along this branch, red and then blue. We just multiply those together. So what is the probability that we get, let's say, blue and then blue again? Well, it's going to be this branch, blue, right? And then we pick another blue, so it's going to be 4/8 times 3/7, which is once again 12 over 56. And now I have to do another one just so we see it's not always 12 over 56. So let's do green and then blue. Green and then blue. The multiplication principle says we can just go follow these branches. Green 1/8, then blue 4/7. So it's going to be 1/8 times 4/7, which is 4 over 56, which we can put here. And then if you went through and multiplied these across, I'll just fill in the blanks what we would get. We would get 6 out of 56. We would get 3 out of 56, 12 out of 56, 4 out of 56. And I'm just multiplying, like to get this 4 out of 56, I'm just going blue branch, green branch, and I multiply the probabilities together. So for this one here, it's going to be 1/8 times 3/7, which is 3 out of 56. And then for the last one, it's going to be 1/8 times 0, which is just 0. I'll put 0 out of 56 just to be consistent with the pattern. And what do you suppose would happen if you added all of those up? We should get a 1, right? So, because it's a sum of all the outcomes of the sample space. These are all the possible things that could happen. You know what I mean? Red, 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 blue, red, green, and all the way through. So these should all add up to 1. So one thing we're going to need to know about is factorials. Some of you have probably seen them before, but I'm sure there are some of you who have not. So factorials, they look like this. They look like an exclamation point, but it's in math, it means factorial. And what it means is take this number, so you write the 3, and then you count back by 1 and multiply them all together. So 3 factorial is just 6. 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. And if you multiply all those together, you get 5,040. So in probability and statistics, these are always integers. In higher math, they don't have to be, but for almost all the applications that anybody but maybe a math major would see, there'll be integers. So it'll be an integer, and then we count back by 1. And then there's also one more that we have to know. 0 factorial equals 1. And this is by definition. So it's not super easy to explain. It is, I mean, it's not terrible, but here's, when you have something by definition, here's an example of one that you would have seen before. So when you were learning about exponents in algebra class, you would have learned something like anything to the 0 power is always 1. Right? I know you guys have all heard that before. And the reason is you define it that way because of this. Because if you've got something like, let's say, 4 to the 8th power divided by 4 to the 8th power, you could say, well, I've got a rule of exponents that says that what I do is I take this power and subtract that power. So you would say that's going to be 4 to the 8 minus 8. That's 4 to the 0 power. And you also know that if you have any number divided by itself, you get 1. So because we started here and we used math that we know works, so we got 4 to the 0. We also started here and got 1. It has to be the case, just to keep things consistent, that these have to be the same. So 4 to the 0 power equals 1. And I just randomly chose 4. It could have been any base as long as they're the same. So then in algebra you would have said, okay, so that's why. So anything with the 0 power is 1. Something happens very similarly here, but it's not quite as easy to show. But 0 factorial is 1. Even though it doesn't make sense like this, just like this doesn't. Right? So when you learned about exponents, again, I'll use this example. If you had 2 cubed, you learned that what this really means is take 3 of these 2's, take 3 of these 2's, line them all up and multiply them together. Right? 2 times 2 is 4. 4 times 2 is 8. So you learned that exponents are a shortcut for repeatedly multiplying. So 2 cubed means take 3 of these, line them up, multiply them together. So if you do that here, the argument doesn't hold. Take none of these, line them up, and I somehow get a 1. So it doesn't really hold, but we know it has to be 1. Same thing here. This, we're defining it to be 1, even though it doesn't make sense by the way we're defining these, like just keep counting back. But for similar reasons, whenever you see 0 factorial, it will be 1. Okay. Also, what about this? If I have 7 factorial, could I write 7 times 6 times 5 factorial? Is that true? Well, it is true, right? Because isn't 7 factorial just 7 times 6 times 5 times 4 times 3 times 2 times 1, and that's what 5 factorial is? So this used to be a really important thing for us to do before we had graphing calculators, because these numbers are huge. I mean, the factorial function is it's said to be a very fast function, means it increases really quickly. So you put 7 factorial in your calculator, you get 5040. Your calculator can't go very high with factorials because it will run out of memory. So you find factorials near where we found that random integer. So on your calculator, to get to factorials, this is what you want to do. You want to press the math button. The math button on the left side of your calculator, far left column, press math. And then from there, go over to probability. So there's some drop-down menus. You can just hit the left arrow button if you want. It'll scroll to probability. Or you can just scroll to the right. And you'll see on number 4 there, it's a factorial symbol. So from probability, then you go to number 4, which is factorial. So to use it, you have to put the number first, then the factorial. So if I want to use the calculator to find 7 factorial, I hit 7, then go through this routine. So I hit 7, math, go over to probability, and then hit number 4 to get the factorial. And then you hit enter, and it should say this. Now, if you experiment a little bit, you're going to see that these things get huge fast. Like, for instance, press 20 factorial once. So if you hit 20, and then math, probability, and 4 to get here, you get a huge number. Basically 2.4 times 10 to the 18th power. One quick note also, in your calculator, when you see this, if you ever have a large number or a real small number, you'll see something like, you'll see, like in this case, I have something like 2.4329, some other digits, but you get to this E18. This E stands for exponent, and it basically means times 10 to the that power. So it's a calculator's way of saying scientific notation. So it means this times 10 to the 18th power, which means basically move this decimal point 18 times to the right. So with a little experimentation, you'll see that if the number is too big, so if you put in 80 factorial, your calculator, it's not going to be able to deal with that number. It's just too big. And it just says overflow. So here's where we can start to see these factorials come into play. So example 3 says, in how many ways can 5 students line up at the door? So let's say you got 5 students. You're going to line up at the door. So we've got 1, 2, 3, 4, 5 spots, right? So let's say this is the front. So here's the door right here. This student's right by the door, first in line to leave. And then this is the second location and so forth. So you've got these 5 students here. They've got weird names. Their parents were not very creative at all when they named them. These are their names. And how many ways can 5 students line up at the door? Well, think of it this way. We've got 5 students here. How many can we pick to go in the first spot? Any of the 5, right? So let's say this student goes in the front spot. So we had 5 choices here. Well, now how many students are left to go in the second spot? Well, now there's 4 left, right? So let's say we pick this student. So that leaves us with only 3 students left to go in the third spot. And we're going to use the multiplication principle here. So we're going to multiply these. We multiply the 3, then the 2, and then finally there's only 1 student left. So you can see that this is 5 factorial, right? It's the multiplication rule, and it's also 5 factorial. So there's a relationship between the two. So in this context, 5 factorial is actually the multiplication rule. So if you multiply this together, you get 120. So you can see how these things get big really quickly. With only 5 students, there's 120 different ways you could line up these 5 students at the door. And you could do a tree diagram too. You could say so let's say we take, for the first spot, we've got any of 5 students, right? 1, 2, 3, 4, 5. Any of the 5 students could go there, and then you've got 4 students on each of these. But you wouldn't want to do it this way. As you can see, this would be kind of a nightmare. By the time you get all the way to the end, you'd have 120 end branches. So it's more intuitive in this case, anyway, just to think of it as a spot by the door. There's 5 students that can go in the first spot. That leaves us with 4 here. And you go right down the line like that. So for our class, let's say we have 29 students. So we've got 29 students. So think the same situation here. We've got a group here, but now we've got 29 names. So we've got these 29 different names here. So we have 29 different names. And we're going to line 5 students up at the door. So, and how many students can go in this very first spot? Well, if there's 29 of them, any of the 29 could go, right? Any of the 29 students could go there. So that means, say, one of these students is gone. So how many students are left to go in the second spot? Well, 28, right? So there's 28 here. Again, this is the multiplication rule. And you would follow that with 27, 26, and 25. And this is a pretty good sized number. So this is 14,250,600. So in a classroom of 29 students, there's more than 14 million ways to just line up 5 of them at the door. And the note here is this is a permutation of 29 items taken 5 at a time. permutation. And we have a counting rule for permutations. So permutations, these are basically the number of ways to arrange in order n distinct objects taken r at a time. And we've got a formula here. And we've got, I'm going to show you another notation too. So if you see this has this n, this permutation, and then the subscript n and r. Another one that's pretty popular, in fact the one that our calculator uses, looks like this. So you'll see this and you'll also see this, but they both have the same formula. So they both use the same formula. This is just an alternate way to say the same thing. So the formula is n factorial divided by n minus r factorial. And the note here, and this is the really important point for these things, is some software issues real quick here. So the note is, put this in red, order matters with permutations. And that can be a little confusing, and if you haven't seen these before or haven't studied them before, it'll be confusing at first, but I've got a really good problem at the end of this section that I think puts everything in place and makes it much easier to think about. So, example 5, they want us to calculate the permutation of 29 items taken 5 at a time. And we can use this formula right here to do it. So this is n comma r, n comma r. So we can calculate this. This is going to be 29 factorial over 29 minus 5 factorial. That's going to be 29 factorial over 24 factorial. And then the way you can do these on the calculator, because like we said, if your calculator has anything like 80 factorial, it can't do it, and it wouldn't be all that unlikely to get one like that. So we're going to do something instead here. So what we're going to do is write this in a way that will allow us to cancel this out. So we're going to write this as 29 times 28 times 27 times 26 times 25 times 24 factorial, right? Because 29 factorial, this works, right? Because this would just keep on going. This would be 24 times 23 times 22. Now, I purposely stopped at 24 factorial because that's what's in the denominator. So in the denominator is 24 factorial. And we know that this is just some number, and this is the same number. So that means that I could just cancel these. And when you do that, it allows you to work with permutations, with larger permutations with the calculator. Now for us, it's actually not going to matter. This is like in the bad old days when somebody, I'm not going to mention any names, took statistics. We had to, they had to use this formula all the time. But in the good old days with calculators like we have now, they all have formulas we can plug in. So instead of just like going through these needless calculations, which don't really have anything to do with statistics, it's just arithmetic, I'm going to show you on the calculator how to do it. The calculator has a command that allows you to plug this in, but I wanted you to at least see how it works. So once we cancel these, we get 29 times 28 times 27 times 26 times 25, and then that's the same as the number we got above, right? That's the same thing. So if you look at the problem above, there's something interesting about permutations. So let me look back here. So when I do permutation problems, applications, for me it's more, it's easy for me to just think of this intuitively. So if I have this question and I'm told our class has 29 students and we're going to line up 5 of them at the door, for me, it's easier just to think, okay, there's 5 spots here, and I just reason through it like this and multiply these together. But other people just like to recognize that this is a permutation of 29 items taken 5 at a time. They don't write any of this out, but they get the same answer, because then they will just use, like before, they just plug it in here, but I'll show you in the calculator how to do it without these calculations. But with a permutation problem, you can do it intuitively like above, or you can go right to the formula. Okay, so now let's look at the way that usually people do these today, like on the TI 83 or 84. So if we want to calculate the permutation of 29 items taken 5 at a time, we just go to the calculator and we have to first hit the 29. So hit the 29, and then we go over to the math menu, and then we need to go to probability, and you can hit the right arrow or you can use left. It's a little quicker because it'll scroll to the left too. So if I just scroll to the left, it'll come around the other side, and then I go down to the second one, NPR, and items permutated R at a time. So you hit that one. And now I put the 5. And there's a couple different versions of software here. So some of you will see what TI calls math print, or sometimes it's called pretty print, where they have the 29 and the 5 be in the subscript location. But it works the same way. You still would hit 29 and then hit the NPR and then the 5. Then you hit enter and you get your permutations. So even though we went over the formulas, because I want you to see the formulas for permutations, but we'll always use the calculator. The permutation formulas are just a bunch of calculations, a bunch of arithmetic, and since we have graphing calculators, they can do a lot of that just brute force calculations for us. So we'll just use the command that you just saw in the calculator when we do these. And I think in the homework they ask you to do a few of them using the formula just to be familiar with it. But on any test or quiz, I would expect you to just use this NPR command to get permutations. And we're going to see very soon there's a similar command for combinations. So let's take a look at this example 6, where we have this breaking news. The officers of the GRCC Stats Club have been announced. And we've got the names here: President, Vice President, Secretary, Treasurer, and CEO. So what if this comes over the intercom, this exciting announcement, and these names are announced, but then they say a few minutes later, wait, we've made a mistake. And then they re-announce the names. And they say, here are the names, you made a mistake before. Now, in this case, this is definitely different, right? I mean, if in this case Jordan is president, over here Jennifer is president. So this lineup, this ordering of these names is totally different from this ordering of names. So the thing to see about this, okay, let's try that again. The thing to see about this is that order matters. So these are not the same. If I change the ordering, it's different. So this is not the same, and that happens with permutations. So there's permutations. When you have a different order and it changes everything, that means you're dealing with permutations. These are two completely different permutations, right? Because you have different vice presidents here. So it doesn't even have to be this much different. Just these two names could reverse. It's going to be different. So every time you change the order, you have a different situation. So in applications like this, where this would be considered a permutation, because when you change the order, everything changes. So the key is, with a permutation, order matters. Changing the order of these names changes everything. So we're dealing with a permutation where order matters. So now let's look at a different situation. So suppose we want to select 5 lucky students to go to GRCC summer math camp. Now before I get all the emails, I just made this up. It isn't real, okay? Every time I mention this, students email like, can I get in? When does it start? How much? Get all kinds of emails. So I just want to stop that, okay? So there really isn't a GRCC summer math camp. I know it sounds awesome, but it doesn't exist. It's just for this story problem. So let's say we get a listing of names over the intercom, and it looks like this. So these lucky winners are announced over the intercom. Say you 5 lucky students have won. They say Tony, Bianca, Nathan, Michaela, and Mike. And these 5 students, of course, are ecstatic. They're like, oh my God, I'm so lucky. And then when they say, oh, wait a second, we're supposed to call them in order of student ID. So then they reread this new list of names: Bianca, Tony, Michaela, Nathan, Mike. So in this case, is anything different? There's no change, right? So in this case, order doesn't matter at all. So a little note here is we could say this is not a permutation, not in this context, because in this context, order doesn't matter. So in other words, when we put this list of names and compare it to this list of names, in this context, they're the same. The order does not matter here. So it's not a permutation. This is actually a combination. So we've got a formula here for the counting rule for combinations. So it says the number of combinations of n objects taken r at a time. You've got this notation here. And now this is a notation you see a lot too, this for combinations. Now permutations don't have a corresponding symbol like this, so this is always combinations. And of course the way that our calculator does it is also fairly popular. We just change this around a little bit. But the combinations have, the formula is a little different. And you can see really all it does, if we ignore this r factorial, we have permutations. So what combinations do is it's a permutation, but that we divide out all the different orderings. So we're going to take a number and divide by r factorial. So think if you have a numerator and you divide it by a denominator, as the denominator gets bigger, the overall number gets smaller. So combinations, there's always going to be less combinations than permutations because you're basically dividing out the different orderings. Because in combinations, when you change the names around, it's not a different combination because order doesn't matter. So a couple of notes here. The first note is order does not matter. So in the example above, when the names were called out in a different order, it didn't matter. It was the same thing. So that's the first note. And the second note, which we just mentioned, was this combination, whatever that is, it's going to be smaller than the permutations for the same n and the same r. There'll be less combinations than there will be permutations. So if we were going to use this formula, if we wanted to do this one by hand, we would have this. So we've got a combination, 29 items taken 5 at a time. So according to the formula, we have 29 factorial over 5 factorial times 29 minus 5 factorial. So again, I'm going to show you how to do one of these by hand. And they probably ask you to do a few of them by hand in the book. But really, we're going to use the calculator. So I'll show you how to do the combinations on the calculator also. But just so you can see what it was like in the bad old days when, not me, but my older friends went to college. we would do something like this. We'd have, so this first step, we'd have 29 factorial, 5 factorial, and then basically this is 24 factorial, right, because we subtract here. So then we do something similar to what we did before, 29, 28, 27, 26, 25, 24 factorial. Just realized I keep saying we. I meant they, of course. Me being way too young. So then these would cancel. And then we'd have this 5 factorial. So we've got, let me put these here, 29, 28, 27, 26, 25. And then the 5 factorial would be like 5, 4, 3, 2, 1. And just to, you just sort of go along and cancel. So I do like the 2 in the 26, right? 2 goes into 2 once, goes into 26 13 times. Then we could do the 3 in the 27. 3 goes into 3 once, goes into 27 9 times. And then we've got like the 4 in the 28. 4 goes into 4 once, goes into here 7 times. And we've got the 5 in the 25. So that goes in there once and 5. And then you just have to multiply all these on the top. So you multiply the 29 times the 7 times the 9 times the 13 times the 5, and you get 118,755. So you basically would multiply 29 times all of these to get this number. So like I said, we do a couple of them just so you know how to use it, but we're really going to use the calculator. So let's take a look at how we would do this on the calculator. We want to find the number of combinations of 29 items taken 5 at a time. We again press the 29 first, then we go to the math menu, and we go to probability. This time I'll use the right arrow key. So press it a few times, get to probability, and then you can see the combinations. That's the third one down. You can see the fourth one down is factorial, which we talked about earlier. So you go to the third one, now you press 5, and you get the number of combinations. And one thing that I may have mentioned also before, if you want to cycle through your previous commands, like if I want to do something similar here, I could just go second, enter, and the last one will come up. Maybe I want to change this to a 8, for instance. So the second enter, every time you press that, it cycles through your previous commands. So it's just something that could save some time. Sometimes when you first are introduced to permutations and combinations, it's a little tricky telling them apart. Like in a particular problem, do I use a combination or a permutation? So hopefully this example 9 will make it a little easier to see. So when we're considering permutations, so with permutations, we're considering grouping and order. When we consider combinations, we're considering only the number of different groupings. Order within the groupings is not considered. So for example 9, suppose there are 12 people who work together in an office. 3 people are needed to serve on a committee. And how many ways can a committee be formed? So first let me tell you, if you are ever, in the future, you're on your job together in a meeting, and you hear something that sounds sort of like you need to form a committee, at that point it's best to look straight down and start shuffling papers. Because if you make eye contact, you're going to be in a committee, which means you have to go to meetings, watch PowerPoint, and drink water, and it's going to be boring. So write that in your notes, save it for future. But for now, we've got 12 people, and 3 are needed to serve on a committee. So think about this. If they say, okay, you 3 are on the committee, and they read off 3 names, if they read them in alphabetical order or reverse alphabetical order, does it matter at all? It doesn't matter at all, right? Those 3 people are going to be set up for boredom regardless of how their names are ordered. So In this case, order does not matter. If you just need 3 people to serve on a committee, it's a combination problem. It doesn't matter how you read the names, read the name by age of the person, by height, alphabetical, it makes no difference. There's the 3 people who are named to be on a committee, and the ordering of their names doesn't matter. So in this case, this is going to be a combination. It's a combination of 12 items taken 3 at a time. Right, so we want to see how many different committees can be formed this way out of these 12 people by taking 3 people at a time. So if you use your TI 83 or 84, you put 12, go to the math menu, over to probability, hit combinations, and then 3, and you should get 220. Okay. So it's a combination because you're just picking a group of people for the committee. Order of the names doesn't matter. Now in this next problem, think about it like this. There's 2 ways to think about this. I think it's easier just intuitively to think like we've got a spot here. We've got a president, vice president, secretary. So there's still 3 people. But we've got a president, vice president, secretary. And if I swap these 2 names, it's different. The names here didn't matter what order they were in, but here they will because you got a spot for this person, a spot for this person, and a spot for this person. So intuitively, with a permutation, I think it's easier to just think, well, we've got 12 people. Any of those 12 could be president. So I'm going to put 12 here. That leaves 11 for vice president, and it's a multiplication principle. And then that leaves 10 for secretary. So if you do it this way, you're going to get 1,320. And again, just to see, combinations are always less than permutations. Now, some people would just recognize this as these. If I reverse the names of these 2 people, it's different. It changes it. So order matters. The ordering of the names matters. So they'll just immediately say, well, it's a permutation problem. And then they punch this in the calculator and you still get 1320. So with permutations, there's kind of an intuitive way you can do it. And there's also, if you just recognize that there's a permutation, you can just punch it in the calculator. You get the same thing. So hopefully this will show you an example where the difference between a combination, where the ordering of the names doesn't matter, just 3 people on a committee, I don't care what the order's in, or in this where the names, the order matters because they've got a little spot to go in. If there's a spot to go in, and if the names are different in those 2 spots and it changes things, that's a permutation. So try them out. They take a little practice, but you'll be able to practice them in the homework. And then finally, we've got the Mega Millions jackpot. So this changes every few years. Before October 2013, the odds of winning were 1 in 176 million. Then in 2013, the game was changed somewhat. Mainly what changes are these numbers here. It was changed so the odds were 1 in 259 million. And then in October of 2017, it was changed again. So before 2017, we had 1 to 75 and then 1 to 15. Then it changed from this to 1 to 70 and this to 1 to 25, and it made the odds worse. So what's happening, you may have noticed, it's kind of a strange thing with the lottery. When the Mega Millions jackpot is at, say, 10 million, they don't sell as many tickets. But all of a sudden when it gets like a crazy number, like 100 million, then everybody thinks, well, 10 million wasn't really worth my time, but 100 million is. So it's just kind of a weird thing. So the lottery officials had noticed that when it goes really high, they sell a tremendous amount of tickets. So what happens is the odds every once in a while become worse, because when the odds are worse, the chances of a giant jackpot increase. So the odds we're going to figure them out, but they're going to be worse than what they were before 2017, which was 1 in 259 million. So they're going to be worse than that. So we can think of it this way. So the way it works, you pick 6 numbers from 2 separate pools of numbers. So the first pool is 5 different numbers from 1 to 70. So you pick those 5, and then 1 number from 1 to 25. So there's a total of 6 numbers, and to win the jackpot, you have to get all 6 of them. So, and there's other, prizes you can win, but to win the entire jackpot, you have to get all 6. So, in how many ways can we choose 5 numbers out of 70? Well, order's not going to matter. You can pick your 5 numbers in any order that you want. I think they typically list them out in order from smallest to largest, but you don't have to pick them in that order. So we're just choosing 5 numbers. Order doesn't matter. So that is going to be a combination of 70 items taken 5 at a time. So make sure you calculate this with your calculator just to make sure that you can, so we get the same number. And you should get 12,103,014. That's how many ways you could pick 5 numbers out of 70. And then how many ways can we choose 1 number out of 25? Well, that one you can just say it's just 25. But if you wanted to verify, you could say 25, choose 1, and you'll still get 25. So the multiplication principle comes up here when they say how many ways can the winning numbers be chosen, because you have to pick this and this. So you need to multiply those together. So you have your 70, choose 5, times your 25, or 25, choose 1. When you multiply these two together, you're going to get a giant number. 575, 350. So this is approximately 303 million. So here's the question for you. If you buy 1 ticket, what is the probability that you will win? That would be 1 over this number. Now, if you're wondering, no, that's not good odds. Okay, that's very bad. You might even have a secret to beat the system. You're like, oh yeah, I'm going to buy 2 tickets. If you buy 2 tickets, then this is your probability of winning. So, turns out I've seen different people do this estimate, but normally when they consider the average distance people live from a lottery retailer, you have something like 7 times greater chance of getting killed in a car accident on the way to buy the lottery ticket than you do of winning the actual lottery. So, probably best to not play the lottery. If you are playing to win, that is. So anyway, that should give you what you need for 4.3. So give it a shot. Make sure you try the homework. And you know what to do if you have any questions. Let me know, right? Email, office hours. Just stay right on top of everything. And let me know if you have any questions.